Psychoacoustics is the scientific study of sound perception. More specifically, it is the branch of science studying the psychological and physiological responses associated with sound, including speech and music. It can be further categorized as a branch of psychophysics. Psychoacoustics received its name from a field within psychology, that is, recognition science, which deals with all kinds of human perceptions. It is an interdisciplinary field of many areas, including psychology, acoustics, electronic engineering, physics, biology, physiology, and computer science. Hearing is not a purely mechanical phenomenon of wave propagation, but is also a sensory and perceptual event. In other words, when a person hears something, that something arrives at the ear as a mechanical sound wave traveling through the air, but within the ear it is transformed into neural action potentials. These nerve pulses then travel to the brain where they are perceived. Hence, in many problems in acoustics, such as for audio processing, it is advantageous to take into account not just the mechanics of the environment, but also the fact that both the ear and the brain are involved in a person's listening experience. The inner ear, for example, does significant signal processing and converting sound waveforms into neural stimuli, so certain differences between waveforms may be imperceptible. Data compression techniques, such as MP3, make use of this fact. In addition, the ear has a nonlinear response to sounds of different intensity levels. This nonlinear response is called loudness. Telephone networks and audio noise reduction systems make use of this fact by nonlinearly compressing data samples before transmission, and then expanding them for playback. Another effect of the ear's nonlinear response is that sounds that are close in frequency produce phantom beat notes, or intermodulation distortion products. The term psychoacoustics also arises in discussions about cognitive psychology and the effects that personal expectations, prejudices, and predispositions may have on listeners' relative evaluations and comparisons of sonic aesthetics and acuity, and on listeners' varying determinations about the relative qualities of various musical instruments and performers. The expression that one hears what one wants or expects to hear may pertain in such discussions. The human ear can nominally hear sounds in the range 20 Hz (0.02 kHz) to 20,000 Hz (20 kHz). The upper limit tends to decrease with age. Most adults are unable to hear above 16 kHz. The lowest frequency that has been identified as a musical tone is 12 Hz under ideal laboratory conditions. Tones between 4 and 16 Hz can be perceived via the body's sense of touch. Frequency resolution of the ear is 3.6 Hz within the octave of 1000 to 2000 Hz, that is, changes in pitch larger than 3.6 Hz can be perceived in a clinical setting. However, even smaller pitch differences can be perceived through other means. For example, the interference of two pitches can often be heard as a repetitive variation in volume of the tone. This amplitude modulation occurs with a frequency equal to the difference in frequencies of the two tones and is known as beating. The semitone scale used in Western musical notation is not a linear frequency scale but logarithmic. Other scales have been derived directly from experiments on human hearing perception, such as the Knell scale and Bark scale. These are used in studying perception, but not usually in musical composition, and these are approximately logarithmic in frequency at the high-frequency end, but nearly linear at the low-frequency end. The intensity range of audible sounds is enormous. Human eardrums are sensitive to variations in the sound pressure, and can detect pressure changes from as small as a few micropascals to greater than 1 bar. For this reason, sound pressure level is also measured logarithmically, with all pressures referenced to 20 microsine Pa or 1.97385 times 10-10 atm. The lower limit of audibility is therefore defined as 0 decibel, but the upper limit is not as clearly defined. The upper limit is more a question of the limit where the ear will be physically harmed or with the potential to cause noise-induced hearing loss. A more rigorous exploration of the lower limits of audibility determines that the minimum threshold at which a sound can be heard is frequency dependent. By measuring this minimum intensity for testing tones of various frequencies, a frequency-dependent absolute threshold of hearing (ATH) curve may be derived. Typically, the ear shows a peak of sensitivity, that is, its lowest ATH, between 1-5 kHz, though the threshold changes with age, with older ears showing decreased sensitivity above 2 kHz. The ATH is the lowest of the equal loudness contours. Equal loudness contours indicate the sound pressure level decibel SBL over the range of audible frequencies that are perceived as being of equal loudness. Equal loudness contours were first measured by Fletcher and Munson at Bell Labs in 1933 using pure tones reproduced via headphones, and the data they collected are called Fletcher-Munson curves. Because subjective loudness was difficult to measure, the Fletcher-Munson curves were averaged over many subjects. Robinson and Dadson refined the process in 1956 to obtain a new set of equal loudness curves for a frontal sound source measured in an anechoic chamber. The Robinson-Dadson curves were standardized as ISO 226 in 1986. In 2003, ISO 226 was revised as equal loudness contour using data collected from 12 international studies. Psychoacoustics has long enjoyed a symbiotic relationship with computer science, computer engineering, and computer networking. Internet pioneers J.C.R. Licklider and Bob Taylor both completed graduate-level work in psychoacoustics, while BBN Technologies originally specialized in consulting on acoustics issues before it began building the first packet-switched computer networks. Licklider wrote a paper entitled A Duplex Theory of Pitch Perception. Psychoacoustics is applied within many fields from software development, where developers map proven and experimental mathematical patterns. In digital signal processing, where many audio compression codecs such as MP3 and Opus use a psychoacoustic model to increase compression ratios. In the design of high-end audio systems for accurate reproduction of music in theaters and homes, as well as defense systems where scientists have experimented with limited success in creating new acoustic weapons, which emit frequencies that may impair, harm, or kill. It is also applied today within music, where musicians and artists continue to create new auditory experiences by masking unwanted frequencies of instruments, causing other frequencies to be enhanced. Yet another application is in the design of small or lower quality loudspeakers, which can use the phenomenon of missing fundamentals to give the effect of bass notes at lower frequencies than the loudspeakers are physically able to produce.